We have a geometric series here because every single term is we're timesing by t every time. So the first thing to do is recall the summation of a general geometric series. Actually, let's just write down a geometric series. Start with the general one. A plus AR plus AR squared all the way up to AR to the n minus 1. This is the nth term because this one is essentially r to the 0. So the formula then is a 1 minus r to the n all over 1 minus r. Notice that sometimes the r and the 1 are swapped around, but when you're dealing with A-level maths and typically convergent sequences where r is less than 1, it makes sense to have it around this way, but you can swap them around if you like on both top and bottom. In our case, we have so very similar thing going on, but a is going to be 1, r is then going to be t, but we're not quite done because the r sequence is slightly different because we don't have t to the n minus 1, we actually have t to the n. So our n as such is actually n plus 1 because you could write this as t to the n plus 1 minus 1, and then it's sort of in this form, but you can see you need to replace that n by n plus 1. So for us, Sn is going to be 1 times 1 minus t to the n plus 1 all over 1 minus t. You could derive this from first principles, a bit like you might have derived the general formula from first principles, and you might prefer that. But for the quickest way to do this is to write down the general one. Just need to observe that there are n plus 1 terms in this sequence, not n terms, and so it slightly needs to be modified slightly. But other than that, the A and the R are quite nice. We're then asked to sum this series here, which is not a geometric series because we're timesing by t every time, but the numbers are changing. So here's the quickest way of being able to deal with this question, and it is to observe that if you differentiate each term in this original sequence, then you will actually get this term here. The hint really is the fact that when you bring the power down, and you lower the power, you can see that's what is actually happening. So let me call this Tn. And actually, I'm going to go straight for it. I'm just going to differentiate this original sequence. And that's going to disappear. That's going to be 1 plus 2t. Then it would be t cubed, so it would be 3t squared n t to the n minus 1. So that is the sequence we've got here. And remember, this thing here is our Sn. So the answer is simply going to be to differentiate this thing here in red. And we can do that using the quotient rule. We have a function divided by another function. So let me call the top u and the bottom v. I'm assuming you're familiar with the quotient rule here. U dash is going to be minus n plus 1 t to the n. And v dash is then simply going to be minus 1. So the quotient rule is u dash v minus u v dash all over v squared. I'm going to quote that without proof. So we're going to get minus m plus 1 t to the n times 1 minus t. minus 1 minus t to the n plus 1. We're timesing that by minus 1. So essentially I can change this to a plus. All over 1 minus t squared. Now, we're nearly there, but it's always good to try and simplify these things, and this will simplify, so you should play around with it just to check if it will. So first of all, I'm gonna write this one first. It's gonna be 1 minus t to the n plus 1, and then it's gonna be minus n plus 1, and then I'm gonna expand this bit out. So it's going to become t to the n minus t to the n plus 1. And then I'm going to need to expand this second bracket out. So basically I'm going to cross multiply it and then bring in the negative. So here I'm going to get a minus, but then there's another minus, so it'll become a plus. Get t to the n, but it's going to be minus t to the n. And then I'm going to get minus t to the n plus 1, but there's another minus, it'll be plus t to the n plus 1. Just about managed to fit that on one line. And this does indeed simplify because I have a minus t to the n plus 1 and a plus t to the n plus 1. So arguably, like, we could just write that down on the final line, and that would be fine. But I'm just going to tidy it up slightly more. So it's 1 plus n t to the n plus 1, because there's a common t to the n term. So I can actually factorize out t to the n, and I'm going to get n here and then a plus 1 here. And you can see if I expanded it, I would get the same thing. So again, you could, you could change this to t minus 1, but actually the top will definitely be like this. That's a pretty neat answer for this thing here. Okay, well done if you got that. All right, let's continue. So we've done this bit, and we've done this bit. T is not equal to 1 through these. The main issue would be that you'd be divided by 0. So hence, find and simplify an expression for this. And if we just compare, we can see that all that's happened is t has been replaced by 3 in all these situations. And then n has been replaced by 2001, because 2001 minus 1 is 2000. So t equals 3, n equals 2001. We can add what looks like, if you're just asked right at the start to add this up, it wouldn't look very easy at all. But now we've done all the groundwork, of which this is quite complicated. I think spotting that differentiation is a key thing, and then manipulating it to tidy it up. But now we're okay, so we can simply substitute in 1 plus 2001 times 3 to the 2002, if I just add 1 to the n, minus 2002 times 3 to the 2001. all over 1 minus 3 squared. Okay, how to try and simplify this, because we're asked to find and simplify. We've found it, but we've not yet simplified. Well, here's the crucial thing. Here we've got 3 to the 2001, and here we've got 3 to the 2002. Like if I had 9 lots of 3 to the 8, and I added 2 lots of 3 to the 8, then I would have 11 lots of 3 to the 8. I can simply add these coefficients together, because it's a bit like doing 9x plus 2x is 11x. It's the same when you add surds. So what I want to do is get it so I've got the same thing. I've got 3 to 2002 and 3 to 2001. Well, we can write this 3 to the 2002 as 3 times 2000, 3 times 3 to the 2001. So my next step is this. All over, now 1 minus 3 is minus 2. If I square that, I get 4. And now this thing here, 2001 times 3 is actually just 6003. So I'm not going to write that all out again. I'm just going to replace it. And then, like I said above, I can do 6003 lots of this minus 2002 lots of this. That's going to become 4001. So it's 1 plus 4001 lots of 3003 to the power of 2001. And you might not think that's very nice, but considering how complicated this summation was, that is a pretty neat answer. Okay, only 1 mark for that, but it was a case of substituting it in and then just cancelling it down. Last little part, question says, write down an expression for both the sums for the case where t is equal to 1. Remember, our formulae that we derived do not apply in that situation, so we're going to need to go back to the start. So I'm going to do it here, in fact, because actually there is enough space. For c, let's go back to Sn, and t is 1. Well, it's going to become 1 plus 1 and so on. Now, like I said before, there are n plus 1 terms. So we've got n plus 1 lots of 1. If I've got 3 lots of 1 added together, I'd get 3. If I've got 8 lots of 1 added together, I'd get 8. I've got n plus 1 lots of 1 added together, so the answer is simply n plus 1. And then I called the other one Tn. This is going to become 1 plus 2 plus 3 all the way up to n. Now this is actually, first of all, it's an arithmetic series, so you could use a formula for it, but actually the hope is that you can identify this as the triangle number. To find the nth triangle number, you add this up. 1 is the first triangle number, then it's 1 plus 2, which gives you 3. That's your second triangle number. Then 1 plus 2 plus 3. And it is worth trying to learn this formula. It's a half n plus 1. That is kind of what the question expects, because it's, you've got time pressure going on. It's only 1 mark to get both of these things. Try and learn that formula for the triangle numbers. Otherwise, you can derive it as normal using arithmetic series. Just a little bit of bonus content if you fancy it. Just going to go back to the original question, and let's say you've forgotten the formula for a geometric series, or you want to be really careful because you've got this n in there and it's not quite in its normal form. So you could actually use the same kind of steps, the same steps as we do to derive the general geometric series formula. If we times through by t, then we get Tsn. When you times this by t, you get t. When you times t by t, you get t squared. When you times t to the n minus 1 by t, you get t to the n. And then we're going to get this extra term when we times t to the n by t, which is this one. We can then subtract these. We can do t Sn. Actually, I'm just remembering. No, sorry. Let me do this one minus this one, which actually we can write down nicely like this. So we're going to get Sn minus Tsn. Well, that can be written like this, Sn and then 1 minus t. And then I'm going to subtract the right-hand sides as well. So I'm going to get 1, and then these cancel, these cancel, these cancel, minus t to the m plus 1. And from this, we can just divide through. Arguably, this is a bit simpler because we don't have to worry about the general formula or anything like that. We just go straight to what we have and use the derivation as a simpler derivation than when you derive the general geometric series.